Hello, everyone. Today we're going to be learning about current and resistance. So, a great analogy for understanding the relationship between current and resistance is say we have a box sitting on the floor here and we want to push it to the right. So, we apply a force F, and then there's going to be a frictional force that opposes that movement, right? So, how does this apply to current and resistance? Well, if we label our box as our electrons, that means that our force applied is the current, because current is the flow of electrons. And then that means that our friction is our resistance. Since resistance is essentially electronic friction, it opposes the movement of electrons. All right, so let's look at a couple other analogies. So looking at the left-hand side here, you can think of resistors as different shaped pipes. So a thicker pipe allows for more water to flow through it, right? Now, you want to think of your water as your current. So if you have a super thick pipe that allows for a ton of water to flow through it, this is essentially a resistor with super low resistance. Now, if we have a super skinny pipe, this allows for hardly any water to flow through it, just a little trickle, right? So this is essentially a resistor with super high resistance. And now here we kind of have a middle ground where it's a somewhat wide pipe that allows for a decent amount of current to flow through it, but you get the idea, right? The thinner the pipe, the more resistance because it restricts the flow of water. And the thicker pipe, the less resistance as it restricts the flow of water much less. Now, you can also think of resistors as like a hill. So if we have a positive terminal that represents higher voltage potential, that can be the top of our hill. And we have a negative terminal, which represents lower voltage potential, that's the bottom of the hill. Now, conventional current always flows from higher potential to lower potential, and that current can be represented as a rock sitting on the top of the hill. So this rock sitting at the top will then roll all the way down to the bottom of the hill, right? So that represents the flow of current. Now, if we were to drastically increase the resistance, the hill would be the exact same. However, the rock would now be much smaller. It'd be like a pebble, for example. So again, that pebble will roll to the bottom of the hill the exact same way the rock will be. There's just a lot less mass or a lot less current flowing through the resistor. Now, if we drastically decrease the resistance, this rock will now become, say, a boulder. It's much larger. Again, still rolls down the hill, but there's a lot more mass or a lot more current rolling or flowing through the resistor. So here we've got a series resistance example. So we've got our 6-volt voltage source that applies conventional current in this direction, goes through R1, R2, R3, and R4. So going back to the pipe example, as we keep adding more and more series resistance, that pipe keeps getting thinner and thinner, restricting the flow of current more and more. How can we prove this? Well, we know series resistors add. So our series is R1 plus R2 plus R3 plus R4 plus all the way until Rn, right? So if we use Ohm's law, we can prove this. So V equals IR. And since these are all in series, we know that the current through them is the same. So we'll represent this as IS. We've got 6 volts equals IS times R1 plus R2 plus R3 plus R4, which the sum of these guys is going to give us 60 ohms. So divide both sides by 60, we get IS equals 1/10 of an amp. Okay? Now let's say we depopulate R3 and R4 and we've only got R1 and R2. So now we've got a series resistance of 30 ohms, which will make this pipe a lot wider. Okay? So again, using Ohm's law, we got 6 volts equals I series times now 30, right? Divide both sides by 30, we get IS equals 1/5 of an amp. Okay, so hopefully you see how the pipe analogy applies to series resistors. Now let's look at a parallel resistance circuit. So we've got our 4 volts here. All 3 of these resistors in parallel will have 4 volts across them. So we can draw a network of pipes, something like this. We've got 10 ohms here, 10 ohms there, and then we've got 20 ohms there, which will represent as a thinner pipe. So you'll notice that these two are much wider, so they'll allow for a lot more current or water to flow through them, right? Whereas the 20 ohm is a lot thinner and it only allows for a little bit of current to flow through. Now, again, we know Ohm's law, V equals IR. We know that these guys are in parallel, so each of them has 4 volts across them. So we got 4 equals IR1 times R1. We've got 4 equals IR2 times R2. And we've got 4 equals IR3 times R3. Now, we can take a look at these resistors and see we've got a 10 ohm, a 10 ohm, and a 20 ohm. And we know that current always takes the path of least resistance. So going back to this pipe analogy, we know there's going to be a lot more current flowing through R1 and R2 because there's a lot less resistance, right? So going back to Ohm's law, we take 4 divided by the resistance. You'll see that R1 and R2 see roughly double the current, which makes sense because they have half the resistance. So let's prove this. So we got 4 equals IR1 times R1, R1 being 10. 4 over 10 equals IR1, or 2/5. All right. Now if we move on to IR2, we know R2 is again 10 ohms. So we've got 2/5 equals IR2. All right. And now as we were just discussing, we should see half the current flowing through R3, right? So we got 4 equals IR3 times 20, which gives us 1/5 of an amp for R3's current.